Hello everyone. This is our second lecture for Chapter 4, Measures of Variability, where we will focus on standard deviation and variance. Measures of variability are meant to describe how spread out data are. Another way to think about this is to describe how far, on average, each observation is from the mean. The most common measure of variability is standard deviation. The standard deviation of a group of scores tells us how spread out the scores are around the mean. To be precise, the standard deviation is a measure of the standard or average distance from the mean. Just as there is a population mean and sample mean, we also have a population standard deviation and variance, and a sample standard deviation and variance. The calculations are different for population and sample data. Here are the steps to calculate the population standard deviation. If we don't know what the mean is, our first order of business is going to be to calculate the mean for the variable of interest. Next, we're going to subtract the mean from each score. This gives each score's deviation score. The deviation score is how far away the actual score is from the mean. The distance separating a score from the mean is called the score's deviation, indicating the amount the score deviates from the mean. Take each data value and subtract the mean from it. X minus mu for population mean. If the deviation is positive, then the raw score is larger than the mean. If the deviation is negative, then the raw score is less than the mean. The size of the deviation, regardless of its sign, indicates the distance the raw score lies from the mean. This means that the larger the deviation, the further the score is away from the mean. A deviation of 0 indicates that the raw score equals the mean. The sum of the deviations in this step always equals 0. Since the sum of the deviations is always 0, the mean deviation or average distance will always be 0. So we need a new strategy to calculate the average deviation or distance. So the next step is to square each of the deviation scores. This gives each score's squared deviation score, x minus mu squared. Once we've squared each deviation score, we then add up the squared deviations. This total is called the sum of squared deviations. The formula is sum of squares, SS, is equal to sigma parentheses x minus mu close parentheses squared. The sum of squared deviations is also known as sum of squares, or SS for short. The next step is to divide the sum of squared deviations by the number of scores. This gives us the average of the squared deviations, called the variance. As you see, along the way to calculating population standard deviation, we get the population variance. Population variance equals mean squared distance, or average squared distance of the scores from the population mean. Population variance measures variability in squared units. The formula for population variance, sigma squared, is equal to sum of squares, or SS, divided by number of scores, nu, or capital N. Why do we square the deviation scores? Well, first, squaring each difference makes them all positive numbers. Remember, the sum of the deviations is always equal to 0. If we did not square the deviations, then we would always divide 0 by the number of scores. Second, it also makes the bigger differences stand out. For example, 100 squared is equal to 10,000. This is a lot bigger than 50 squared, which is equal to 2,500. And third, squaring the differences make the final answer really big and harder to understand. It is difficult to interpret because it is measured in squared units. However, variance plays a really important role in statistical inference, as you will see in later chapters. Remember that the goal here is to calculate a measure of the standard or average distance of the scores from the mean. So the next step is to adjust for having squared all the differences by taking the square root of the variance. The standard deviation is the positive square root of the variance. Now, there are two ways to calculate the sum of squares, the numerator of the variance and standard deviation formulas. One way is what I just covered, where we calculate each deviation score, square each of the deviations, and then add up the deviation scores. This is the definitional formula for sum of squares. All of the textbooks use this formula. However, there is an easier way to calculate sum of squares called the computational formula. This formula leads to less calculation errors. The first step is to square each score and add the squared score. So sigma open parentheses x squared close parentheses. The next step is to add up the scores, square the sum, and divide it by the number of scores. Open parentheses, sigma squared close parentheses squared divided by n. Then subtract your answer in the second step from your answer in the first step. The formula is SS is equal to sigma, open parentheses, x squared, close parentheses, minus, open parentheses, sigma x, close parentheses, squared divided by n. Remember that this is just the numerator of the formula and not the final answer for variance and standard deviation. We would still need to finish the calculation and divide sum of squares by n to find the average squared distance from the mean, or population variance and standard deviation. I will show you both of these formulas in action so you can see the difference between the two.